So at strong coupling, one can compare down-to-earth field theory calculations with string predictions of holography, and this is basically the core subject of my talk. So the theory turns out to have a non-trivial phase structure, which is depicted here. So on the horizontal axis is the 't lambda, and vertical axis is mass. It's a dimensional parameter, so we need to multiply it by some scale. So as such scale, I will take the radius of compactification on S4, which then would depend on a dimensionless coupling M times R. And so if in the conformal regime where the radius of the sphere is very small, this is not different from n equals 4, so the mass is not important. And it interpolates between the weak coupling perturbative regime and the strong coupling regime, which is described by string theory in ideas 5 x S5. Now, if we go to larger radii, we expect the same. So at weak coupling, we have perturbation theory. And at strong coupling, there should be some holographic description. Now, if we go to larger and larger radii, it turns out that the perturbation theory starts to be contaminated by large logarithms. And this is because if you take, weak coupling is the same as, if you take large mass, in some sense we can forget about the hypermultiplet, we can integrate it out, and this would leave a pure n equals 2 theory, which has a running coupling, and so these logarithms are simply arise from the beta function of n equals 2. So this corner is described by n equals 2 theory. If you do the same at arbitrary coupling, it turns out that we can end up in a different phase. So the theory possesses a non-trivial phase structure in the infrared when we take the compactification radius to infinity. And moreover, these phase transitions accumulate to strong coupling. So it seems that this holographic point described by Pilch-Warner solution is obtained when is very complicated because it's an accumulation point of infinite number of phase transitions. And so one motivation for our work was to understand how these phase transitions are described holographically, and well, we failed to do so, but still we could get a very precise match between supergravity and string theory and field theory calculations that are based on localization. So the starting point is, for me, is the partition function on S4 that was computed by Peston in 2007 by the method of supersymmetric localization. So the partition function has a form of a matrix model in the eigenvalue representation. By the way, for n equals 4, this would be just a Gaussian matrix model, but when we add mass, there are interactions. And so they have a form that is under control, and they all can be calculated. So this is the starting point of our analysis. H here is some complicated function that can be represented as an infinite sum. So it's a pretty explicit answer. And I should say that this is probably the only point of contact with integrability, because matrix models are assumed to be integrable in some sense. And the idea is that we just solve this matrix model at large n and arbitrary lambda, and this will give some non-perturbative information about n equal to star theory. So of course the most interesting regime, so this formula is written on a sphere of arbitrary radius. R doesn't appear here because it is dimensional parameter. So actually the integration variables here are eigenvalues of the scalar field in the vector multiplet. They have dimension 1, and so does mass. And it is assumed that they're all multiplied by R. So all entries in this formula should be understood as A times R, M times R, and so on. So the interesting regime is the decompactification when we take radius to infinity. So this is, then we recover theory in flat space. This is similar to what Zohar Komargodski discussed in his talk. Although he discussed conformal theory, and their correlation functions on the sphere are more or less equivalent to those on the plane, but here theory is not conformal. So there is an explicit dependence on the radius, and to decompactify we need to take this into account. And so after, well, as usual in matrix models, the large n limit gives some integral equation. In the decompactification limit, that equation simplifies. And let me just write down the result. So it's a relatively simple equation. I know how to solve it exactly in elliptic functions when mu is sufficiently small, but not for any mu. So mu here is the width of the interval in which the density, rho is the density of eigenvalues. It is defined on some finite interval of the real axis. And so this equation has a unique solution that's normalized to 1 for any mu. So there is a contradistinction to the matrix model case where actually the normalization condition fixes the width of the interval. Here it does not. It's easy to understand why. Because the equation is homogeneous, so we can multiply rho by any constant. And so this constant is fixed by normalization condition. All right, so so we need another condition to well, to find mu, because mu is an emergent parameter. So the parameter that defines the theory is the coupling, and there is an equation that relates mu and lambda. So it's an integral condition on the density. And so one can view this condition as, so a useful way to look at this condition is that we solve equation for any mu, substitute the result here, and then we find lambda as a function of mu, or we can invert this function, and then we can find mu as a function of the 't Hooft coupling. So this equation contains a logarithm, and this logarithm can be actually identified with the beta function, with the RG logarithm of n equal to 2 theory. So how does the solution look like? Well, one can look at the equation and see that the qualitative picture of the density will be as follows. So the density is defined on some finite interval, and of course it has singularities at the boundaries of the interval. So here the singularities are of inverse square root type. At the boundary of the interval, the density will be singular, will go as 1 over square root of mu minus x. But then, if you look at the equation, there are 3 terms, and so this terms is consistent with the singularity structure, but these two terms are not, because they contain an argument shifted by m, and so there will be an induced singularities in the middle of the interval, if the interval is sufficiently large, which are shifted from the endpoint by m. So if, let's see, if this is m, then there will be a singularity at mu minus m. Try to figure out. And then at mu minus 2m, and so on. And there will be singularities at the images of the other endpoint. So in total, the density would be a piecewise continuous function. Roughly of this shape. In general, there is no analytic way to calculate the shape of this function, but one can reduce the problem to some equation that can be very efficiently solved numerically. And then at strong coupling, one can do a systematic expansion in 1 over lambda. So let me write down the result for you. So this is the most interesting regime where the coupling becomes strong. So what happens is that the density there drastically simplifies and becomes that of a Gaussian matrix model. So this is Wigner distribution. It's just the same as what one would get in a matrix model without interaction terms. It seems that it's not really well consistent with the picture I was trying to advocate, because of course this distribution is absolutely smooth in the middle of the eigenvalue interval. And secondly, it also goes to 0 at the boundaries, whereas the true distribution starts at infinity and also has branch points in the middle. But the point is that at strong coupling, the boundary of the interval in fact, becomes very large. So so one can calculate it in the leading approximation, and you see that it grows with lambda. So in particular, at very big lambda, it becomes much bigger than m. So there are many, many intervals of length m that fit into this into the eigenvalue distribution. And so these branch points, they are densely fitted into the eigenvalue integral. And so in practice, if we magnify the distribution, for instance, if we magnify this region near the endpoint, then what we will see is this very complicated structure with many singularities, whereas the distribution that is Gaussian is simply an average distribution over sufficiently long intervals. So near the boundary, the distribution of eigenvalues still has a lot of singularities. But if you average over this short distance structure, then the average is what is drawn here. So, so this distribution arises when we average over very strong small scale fluctuations. One can actually find an analytic formula for this near endpoint distribution. Let me write it down. Just for the record. So this function depends on x only through this parameter psi, which is a fractional part of the distance to the interval. So so the function is sort of periodic, but the summation here goes up to the integer part of this variable. So at the end we get this picture. And now it turns out that if you want to compute the next correction to this formula, it comes from this near boundary region. So at the next to leading order, at strong coupling, mu is gets a correction. Which is, well, relatively simple. So this term is, well, essentially a Gaussian result. And this is a boundary contribution from the region where, well, the density cannot be really approximated by the Wigner distribution. So what do we gain by knowing these results? What observables can be calculated in this theory? Well, one thing that one can compute is a Wilson loop that's running around the big circle of S4. But then we take the compactification limit, so this Wilson loop becomes really huge. And basically, any sufficiently large Wilson loop can be calculated within the same approximation. So so the Wilson loop operator as an n equal 4 superrank Mills, it is defined by adding a scalar field to a gauge connection. So it contains an integral of I a mu x dot mu, but there is also a term which couples to the scalar field. And now what happens is that this scalar field condenses, so it acquires an expectation value, which is described by the eigenvalues of the matrix model. And so to some approximation that is the leading approximation for large contours, we can simply substitute the expectation value to this field, of this field to this formula, and disregard all other quantum corrections. This is actually true for the fundamental representation. For higher representations, the story is a little bit more complicated. But anyway, so at the end, the formula will be just a convolution of the density of eigenvalues with the exponent, with the exponential whose exponent is length of the contour times well, the eigenvalue. And if you are interested in, so I should say that the status of this formula is the following. For a circular loop on the fourth sphere, this is an exact result. For any other contour, this is approximation that is, in some sense, it can be justified qualitatively, but there is no proof. But then we expect that Wilson loops of that are sufficiently big will be universal. Confining theory, they would be satisfy the area law. This theory is not confining. So the Wilson loops actually satisfy perimeter law. And so if you take L to be very large, so this integral will be picked, the integrand is picked at the endpoint. So the expectation value of the Wilson loop is given by the perimeter law with the coefficient that is the parameter mu that we can extract from the matrix model. So we conclude that Wilson loops in n equal to star theory satisfy the perimeter law. And with calculable coefficient, which I will call an effective string tension. Well, you may say that it's non-confining theory, there are no strings, but we know that this theory is described by string theory. It's strong coupling. Well, one lesson of ADS safety duality is that string theory does not imply confinement, so it depends really on the dual geometry. And the dual geometry here is such that the area law for strings in the bulk is the perimeter law on the boundary. So the coefficient of this perimeter law is then the effective string tension. So if you want to make it dimensionless, we divide by the mass scale of the theory. And then from the result of the previous calculation, we find that at strong coupling, the answer is square root of lambda divided by 2 pi. And this is, of course, the familiar formula from ADS-CFT duality. The ADS-CFT dictionary tells us that dimensionless string tension is related to coupling by this formula. So now we can also compute a correction to it from the matrix model, and presumably there are, well, not presumably, but certainly there are higher order corrections which we have so far not calculated. Now another object that one can calculate here are Wilson loops and high representations. So, for instance, one can take a Wilson loop that is defined in a symmetric representation with k boxes, and then k is another parameter that we can dial, and so it is useful to well, have another object that we can calculate, another function of an extra parameter. So an interesting regime is when this parameter scales with n. And so then we cannot, so if k is small, then this is simply given by large n factorization formula. But if k is of order n, we cannot use large n factorization anymore. So how to calculate this such a Wilson loop? So for the fundamental Wilson loop with one box, the answer is given by the largest eigenvalue. The same is true for the Wilson loop in the symmetric representation, but now we need to take into account exceptional eigenvalues that actually get off the bulk eigenvalue distribution. So, so the eigenvalue distribution is, well, it's some Gaussian. It means that the eigenvalues are most of the eigenvalues are sitting somewhere between minus mu and mu. But of course, there is a non-zero probability to find an eigenvalue outside the interval. Let's call this its position A. Well, this event is very improbable. So the probability to find such large eigenvalue is suppressed exponentially with n. Where f is some calculable function that is determined from the matrix model, and it can be calculated explicitly. For the fundamental Wilson loops, this events where the largest eigenvalue is off the bulk distribution were not important, simply because the answer is suppressed exponentially with n. But now for Wilson loops that have k boxes, the weight in the integral is exponentially large, and there is a competition between the Wilson loop itself and this small probability to find an eigenvalue outside the interval. So the formula at the end looks like that. This is, I believe, is true when L times M is sufficiently big. So anyway, then one weighs this factor that comes from the Wilson loop against the probability to find the largest eigenvalue, and there is a saddle point. And so in the regime where K is of order n, and both go to infinity, and when the length of the contour is very big in natural units, the Wilson loop in case representation is given by square root lambda by a simple exponent. Well, actually, this is equivalent to Lagrange factorization formula that would tell us that the K-symmetric representation Wilson loop is the K's power. I would like to emphasize that this is a non-trivial fact. It's only true in this regime. And only in this theory, for instance, in n equal 4 super-Yang-Mills, this would not be correct. So these are the observables that can be calculated from localization. Now the question is, can we compare them to string theory? Let me show you how we can calculate the same observables using holographic duality and compare. So these formulas were obtained from localization, so this is an explicit evaluation of the path integral in the theory. But then we can compare them with holographic formulas that, well, that are less justified in a sense. So what is the holographic dual of n equal to star theory? This is a background that should contain some mass scale, because the theory has a mass scale. And as usual in ADS-CFT, mass scale maps to some object in the bulk. So black hole horizon would be dual to temperature, or just some sharp cutoff. But here it is at the main wall. So near the boundary, the background asymptotes to ADS5 cross S5. So if this is a spatial direction and this is a holographic direction, normally it's, in this context it's denoted by C. Then there is some relatively sharp transition from the asymptotic ADS5 geometry to geometry that's actually can be identified with ADS6, in quote unquote. So it's still a it's not a product, it's a work product of something 5-dimensional and and the sphere and the deformed sphere. But anyway, so the distance, coordinate distance to the defect, to the domain wall, defines the holographic dual of the mass scale of the theory. And so this is the way how it arises in holography. So let me write down the metric. It's actually a slice of this 10-dimensional metric. So the claim is that, so here A of C is a known function, and some, well, it's not very complicated, but I'll not need it, so I'll not write it down. Anyway, so this function goes to 1 when C goes to 1. And the claim is that this is actually ADS metric written in some probably not very familiar coordinates. If one does a coordinate transformation of this form, then Z will be the usual holographic radial coordinate in Poincaré-Patch ADS. So to compare to localization results, we want to compute a Wilson loop expectation value in this geometry. And so Wilson loops, according to holography, they satisfy area law. So we need to draw a contour on a boundary and then find the minimal surface whose boundary coincides with this Wilson loop. Dilaton grows. So it starts at constant value that defines the coupling asymptotically in ADS5, and then it grows. So in principle, far away in this ADS, we run into this region where dilaton is big, so that's, the string theory becomes strongly coupled. But, okay, that happens asymptotically far away in the geometry. All right. So what is the area law in this geometry? Well, the area, actually it's very easy to compute the area. We don't need to solve for the minimal surface as soon as the Wilson loop is sufficiently big. Well, the reason for that is following. Of course, the metric is biggest near the boundary. So to minimize the area, the surface would try to do nothing in the beginning. So it will start off as a cylinder, and then it will slowly close off away from the boundary. But the point is that this region where it's kept off and closes produces a very small contribution to the area. So most part of it comes from this cylindrical region where we can simply assume that the geometry of this minimal surface is a tensor product of a line, vertical line, and the contour itself. And then we can simply use this as an induced metric and calculate the area by integrating MDL dc and then the square root of product of these two factors. And so the square root is c squared minus 1 to 3/2. And so we need to integrate this from 1 to infinity, but at 1 the integral diverges. But as usual, we need to regularize. So it's not actually 1, but we need to cut off the integral from in z at z equals epsilon, and then subtract whatever divergences in epsilon occur. This is the usual holographic renormalization prescription for Wilson loops. So if one, well, this is an elementary integral, and so it produces the divergent term that has to be subtracted, and then a finite remnant which is minus m to the L. So this is regularized away. And the rest should be substituted into the exponent of the Wilson loop, so which is, well, minus square root lambda over 2 pi times regularized area. And so altogether this gives e to the square root lambda m L divided by 2 pi. So we get the perimeter law with the coefficient that matches with the field theory prediction. All right. So, but in field theory, we know now a little bit more. We know also the next coefficient. So the question, where does this shift by 1/2 come from? And the answer is that it comes from string fluctuations. So if you consider deviations from the minimal surface, well, I first saw similar formula in 1998. Since then, I got used to it. So, actually, it's a theorem that it should be negative. All right, so if you consider the setup that one can consider is that, well, as you see, this perimeter law is valid universally for large contours, so we can simply take the straight line of large lengths. The minimal surface then is just, well, is plane in the bulk, but then we can consider small fluctuations of the string around this plane. So let's say the deviation is xi, and then the string action will decompose into the classical part, and then some quadratic part in xi. And then we integrate out the xi's, so the string path integral, which is the Wilson loop, will be equal to e to the minus s classical. This gives the area law. But then there will be a ratio of determinants for fermions and for bosons. Now, if we denote this direction by tau and this by sigma, then in the tau direction we have translational invariance. So all the determinants will be exponential in, well, in the lengths, as they should. So typically, logarithm of determinants that arise will be proportional to L times the integral d omega over 2 pi. So now we also have P, which will be momentum in the sigma direction. But then in the sigma direction, of course, this fluctuation has a potential, right? So there will be some this operator will contain some non-trivial potential that actually would push this fluctuation back to the boundary. And so this potential would produce a phase shift, and the well-known formula for the determinants relates the phase shift to the density of states. And so for the modes of mass m, the formula will be like that. And integrating by parts, one can simply express all these determinants through the phase shift. So the final result will be a sum, really? So will be a sum of the phase shifts. And we only could calculate it numerically. But at the end, so the result numerically is consistent with being simply 1/2. So for this, well, we actually got a 0.4.9 something. But anyway, so it seems that string theory is in agreement with the explicit field theory calculations. I'll not describe the higher representations because I don't have time, but they're described by d-branes in the bulk, and one can construct a relatively simple solution that also reproduces the action of the D3 brane in the bulk, reproduces the exponent of the Wilson loop in the symmetric representations. Thank you very much.
Can you just make the correction coming from the fact that the dilaton is not constant?
It's a good question. So, in principle, there is Fradkin-Zeitlin term in the action. It's the same order as determinant corrections, but we didn't take it into account. So the correct prescription seems to be that, well, roughly speaking, so my interpretation of this is that Fradkin-Zeitlin term takes into account the difference between ghosts and longitudinal modes, and we didn't make any distinction. So probably it just cancels with this ratio of determinants.
Thanks for being on. What I didn't get to the very beginning was that you were studying when you were looking at the eigenvalue model in localization. There was no R in it. How did you take this to contact?
R was so the integration variables had dimension full. So these are eigenvalues of phi, dimension 1. So to save space and time, I denoted them by A, but in principle they're A times R, which is dimensionless. So all these functions that enter the localization path integral are functions of A times R. So, and M times R.
What's the R to infinity limit now?
Well, the R appears explicitly everywhere, so you take R to infinity. And
But it should be a combination of M and R, something dimensionless.
yeah, sure. It's M times R to infinity, going to
So it
infinity.
was really the N times R to infinity.
Yes.
So, are there any other observables which you can compare in the scene? So this is conformal theory. In conformal theory, we have some two disjoint axioms that we can compare correlation functions, primary operators, and the boundary with
well, one can think of many possible observables, but one cannot calculate them. So this is as much as we can calculate explicitly from localization. Correlation functions would be, in a sense, more interesting, but localization cannot predict them at any coupling. And the theory is probably not integrable, so one cannot do much when lambda is large. But holographic predictions for correlation functions are kind of interesting. So what happens to this theory is that it flows to a conformal point at strong coupling. But this conformal point is it's a four-dimensional theory with five-dimensional properties. So it has all the features of a five-dimensional CFT. So how that comes out of field theory, well, I don't know. We have a hypothesis that this is through Iguchi-Kawai mechanism, but one cannot check it with 100% rigor.
Okay, maybe one final question over there. Since you consider high representations of Wilson movement, could it be so high that it creates a black hole-like object?
That one potentially one can study that, but so we studied. There are three regimes. So the representation of size 1, representation of size n, and this is what we studied. And black hole would be representations of size n squared. So those would actually deform the saddle point of the matrix model.
Can it be still, can the exact calculation be available still by localization then?
Potentially, yes, but yes. So the path integral still reduces to a matrix model, but now the observable itself should be taken into account when computing the saddle point. As to the best of my knowledge, no one has done this, even for this a simpler setup where the matrix model is Gaussian, n equal 4 superannuals. And it's a very interesting problem. I agree.
Okay, so let's think